Well, welcome to the video on permeability modelling. What we'll do is have a look at two of the most common permeability models, but before we do that, I'd like to put them into context in terms of how we use the permeability, which is normally in Darcy's law, and in this particular slide here there are these four things that I'd like to ensure that we're all happy with before going on. The first one is the usual description of voidage and solid concentration summing up to equal to 1. So these are volume fractions. So this is the voidage or void fraction, or also known as porosity, and that is the volume of voids divided by the total volume of the bed. Here's an example of the porous media that is constituted by the solid particles in a sort of red colour and the voids that you can see between the solid particles. The solid concentration again is by volume, so the solid fraction, big capital C, uppercase C, is the volume of solids divided by the volume of the bed. So you have the volume of voids divided by the volume of the bed, just here. We have the volume of solids divided by the bed, just here, and as they're volume fractions, they must add up to unity. Either you've got solids in the bed or voids in the bed. Okay, so that's our porous, should really be porous medium. Media is a plural. So here is our porous medium. Okay, so that's the porosity and voidage. Readily interchangeable, just 1 minus C for voidage or 1 minus epsilon for solids concentration. Relatively simple to convert between the two. Now what about superficial velocity? Well, the superficial velocity is illustrated just here. We normally use the symbol U0 for superficial velocity. It's the volume flow rate, because V is volume and T is time. So it's the volume flow rate divided by area. Sometimes you'll see it simply Q, which is conventionally used for volume flow rate divided by A, and A is the cross-sectional area, so it's the full cross-sectional area of the empty tube. That's what we mean by superficial. Superficial means on the face of it, and that's exactly what we have. The liquid is coming in here on the face of that porous medium. We have a certain flow rate Q. If we divide by the total area, then that gives us the superficial velocity of the liquid as it comes in, or the fluid rather, as it comes into the tube and just before it goes into the porous medium. And then we have the interstitial velocity, which is what we have just here. The interstitial velocity will be faster than the superficial velocity because the area is reduced. As the areas come from the area before the particles into the area where the particles are present, A prime is going to be much smaller than A. That gives far fewer space for the liquid to flow, and according to continuity the velocity is then going to have to go up because we have the same volumetric flow rate going through the porous medium, and the only way it can do that is if the velocity, the interstitial velocity, goes up because the area over which it can flow comes down. So there is this simple relation between the interstitial velocity and the superficial velocity. It's simply U0, the superficial velocity, divided by the voidage, or epsilon. And then of course when the fluid comes out of the porous media again, as described just here, the velocity will be the same as what it was superficially, so U0 exists below just here. Okay, well let's look at Darcy's law, and the analogy that I'm going to draw here is with the electricity flow. Okay, so just here we have Ohm's law at the top here, where V equals IR is a well-known equation. It's been rearranged here to V equals RI for reasons that will become apparent. V is of course the voltage, the potential difference if you prefer, So potential difference, and it's this potential difference which is proportional to the current. Typically you'd measure that in amps. Okay, now the amount of current that will flow depends on the resistance of the circuit. So with these two resistors of equal resistance in just here, and if we start off with a total potential difference of 1.5 volts, and with two equal resistances here and here, then the potential difference will be 0.75 volts, half the voltage, before we go into the second resistor. Okay, so here is our battery that is obviously driving electrons around the circuit, and we've got an equal voltage difference over these two resistances, and that is exactly analogous to what we have in fluid flow. Here is our pump. The flow, in fact, in this case is going to be in this way around, having left the centrifugal pump from the top. Same sort of principle though. If we have equal resistances to flow, in other words the same permeability in both of these porous media, then just as we had for voltage, we're going to halve the pressure. So the delivery pressure from the pump is 20 kilopascals, will be down to 10 kilopascals here, and then down to 0 kilopascals here. And then we've got a nice circuit that goes round and round in much the same way as the electricity did. Right, well, let's turn our attention to the constitutive equation. This equation here is analogous to our V equals IR. First of all, let's consider the pressure gradient. Delta P, our 20 kilopascals here, divided by the length, which is, well, if we assume negligible pressure drop in the piping, then it'll be the combined length of these two. If we're looking into the total pressure drop, it would be combined length of these two resistors. If we're looking into just the pressure drop over one of these columns, then we just want the length of one of the columns. But here is the driving force, the driving potential for the process, and that of course is exactly analogous to our potential difference, our voltage. So that is our driving force for the process. What about the analogy for the flow? Well, the analogy for the flow is quite logical. It's the V is volume, T is time, 1 over area. So that becomes actually a velocity rather than a flow. But it's clearly related to flow because V is volume, so it's a velocity, or Q over A, and that is directly analogous to flow of electricity. So what was amps in Ohm's law is of course now meters per second. It's the superficial velocity of the fluid as it enters the porous medium. So that leaves us with the term here, mu over K. Mu over K. What is mu over K? Well, mu is the coefficient of dynamic viscosity of the fluid, and K is our permeability. And that there, mu over K, is analogous to resistance. But instead of resistance to the electron flow, we're now talking about resistance to the flow of a fluid. Now, does that make sense? Mu is on the top, mu is the viscosity. The more viscous the fluid, the higher the resistance. That makes a lot of sense. So treacle is a lot more difficult to pump round than water. What about permeability? Well, that exists on the bottom, and if something's more permeable, it'll have a lower pressure drop because it exists on the bottom of the equation. Again, that makes an awful lot of sense. So it does make sense that the resistance to fluid flow is a property of the fluid, that's the viscosity, divided by a property of the solids inside the porous media, that of course being the permeability of the porous media. So the two equations, our two equations, the Darcy's law, which is what this is just here, is directly analogous to Ohm's law, Both equations are simple linear equations. If you want more flow, be it of current or of liquid, then you have a proportional increase in the driving pressure required, which could be potential difference for electricity or pressure drop in the case of a fluid. So that proportionality is very much illustrated here. The consequence of Darcy's law is we were expecting this linear increase of pressure with flow rate, and of course there is no offset, there is no constant, so it'll go through 0, 0. At no flow we have no pressure drop. Now pressure gradient, delta P over L, is in fact a vector quantity, as indeed is velocity. Okay, so these two, pressure gradient and velocity, are vector quantities. So and they act in opposite directions. So in fact, we should really have a minus sign in Darcy's law, but it just complicates things for most calculations, because in most calculations we're just interested in the scalar property, what is the pressure drop, rather than the concerning ourselves about the gradient, pressure gradient, and the direction that acts in. So we tend to drop the minus sign out to make life simpler. However, if doing a derivation, if adding other equations to this, then that minus sign can be very important. Otherwise, the derivation might not be quite as robust as otherwise it should be. I mean, Darcy's law is such a simple linear equation. It's hardly surprising that it was observed to be the case a long while ago, in 1856. By Darcy looking at the flow of water through filters outside Paris. And as stated before, it's simply the driving potential is equal to some resistance term times by the flow. And that is similar to the Ohm's law, as we saw a few seconds ago, the Fourier heat conduction equation, Hagen-Poiseuille for flow of fluid through a pipe. They all behave in exactly the same sort of way, where you need an increase in flow rate, you have to increase the driving force or driving potential. So they're all similar sorts of equations in that respect, simple linear equations. Okay, so we have our Darcy's law just here, and I mentioned it's analogous to the Hagen-Poiseuille, which equation is just here. Again, we have the viscosity on the top there. The diameter here in Hagen-Poiseuille is the internal diameter of the pipe. Everything else is the same, so as in Darcy's law. So in fluid flow through a pipe, it's the internal diameter squared. So by looking at the two equations, clearly we're anticipating that the units, the SI units of permeability, must have the same dimensions as diameter squared, and that means that permeability has the units meters squared, and that is in fact the case. Okay, another comparison to do is the comparison of Darcy's law to the Kozeny-Carman equation. I'm not deriving the Kozeny-Carman equation, you can see that in the textbooks. I'm only commenting really on the Kozeny-Carman equation. First thing to comment on is that clearly what we have here is inverse permeability, because the Kozeny-Carman equation has the same left-hand side as Darcy's law, the same right-hand side as Darcy's law after the resistance term. So clearly the square brackets are the resistance to flow term, which is the inverse of permeability. Okay, so we've still got viscosity out here, so this is just, the square brackets is just the inverse permeability. So what do we have in the Kozeny approach to permeability? What's inside the square brackets? Well, the K term here is the Kozeny constant, and that textbook value is 5, but I'll say a little bit more about that in a moment. Then we have 1 minus the one minus the voidage. In other words, that is the solid's concentration squared. 1 minus the voidage squared, or the solid's concentration squared. Then we have specific surface area per unit volume, again squared. Okay, don't forget that has units of meters to the -1, so that correctly puts meters squared onto the bottom, because it's meters to the -1. So the higher the specific surface area, then the greater the pressure drop will be. That's logical, because the higher the surface area, the more friction there will be as the liquid flows through the porous media. More friction means more pressure drop. Then on the bottom here we have the voidage cubed, or 1 minus capital C all cubed, 1 minus concentration all cubed. Additional thing to point out here is that this is assumes no turbulence in the fluid. So we know that this is only valid for a Reynolds number, which is always the ratio of inertial to viscous forces that is less than the appropriate amount for the threshold of turbulence. In our case, this is what we call the modified Reynolds number, not the flow Reynolds number of Hagen-Poiseuille, but the modified Reynolds number, and the threshold is 2, not the 2000 that we see in flow-through pipes. So this equation is only valid, becomes less and less valid as the modified Reynolds number becomes greater and greater than 2. Okay, and that's true of the Kozeny-Carman equation and Darcy's law. They are both linear equations, so therefore they are both laminar flow equations. Okay, so how do we use Kozeny-Carman equation? Why do we use Kozeny-Carman equation? I concentrate a little bit here on design, but there's much more to it than just design. But supposing we needed to work out the pressure drop for a given flow rate, just like we might do in pumping fluids around pipes. Well, okay, if the flow is sufficiently laminar, negligible turbulence, then we can use the Kozeny-Carman equation. Okay, so how do we put some numbers in here? Well, we're going to have to use probably a book value of 5 for the Kozeny constant. Clearly, the specific surface area per unit volume we can relate to the SOTA mean diameter. So that's 6 over x, and that's where x is the SOTA mean diameter. Okay, and of course that's all squared. So if we know what the particle size is, or at least the SOTA mean diameter is, then we can work out the specific surface. The other thing that we're going to need is, of course, the concentration, or epsilon, the voidage, which of course is 1 minus the concentration. So if we know what the concentration of the porous media is, we can work out what the voidage is. We can use the equation as given here. So in a design, from that given concentration for, let's say, a packed column, we know the concentration of the packing is typically 50%, so C would equal to epsilon equals 0.5. That's a fairly typical value for solid spherical particles. Concentrations are much lower than 0.5 with ground material. And in biological material, C can actually be down to very, very low values, but for columns it's typically 50% or 0.5. So we can now use this as a design equation. It goes beyond just design though. We can also model a process, and that enables us to potentially control a process and certainly do the what-if type scenarios. Supposing we double the flow rate, obviously we're expecting a double the pressure drop, but what if we actually change the particle size, for example? So if we change the XSV, what difference is that going to make on the total pressure drop? Well, you see it's squared, so the change in the particle size would have a pretty major effect on the pressure drop. Gives us the ability to do the what-if scenario of an existing process, not just designing a new process. Okay, well, I said I'm not going to derive the Kozeny-Carman equation, and I'm not, but I do want to talk about two of the most important aspects that are within the derivation. In other words, what did Kozeny bring to the party? In Fundamentals of Particle Technology, this is equation 3.2. It's in chapter 3, and it's this definition of a flow channel. You remember that Darcy's law is pretty analogous to Hagen-Poiseuille. So in Hagen-Poiseuille we have the internal diameter of a pipe. And that's analogous here to the volume of voids filled with a fluid, which would be in total the volume of voids filled with a fluid. So if epsilon is the voidage, L is the bed depth, and A is the cross-sectional area, then LA is the volume multiplied by the voidage, then that's the volume of voids. And then we have the wetted surface area. So again, if we have the volume of the process, but now we want to multiply by the solid concentration, which is 1 minus epsilon. And why do we want to do that? Because that's now the volume of solids. So if we multiply by SV, the surface area per unit volume, then that gives us the surface area of the process. Okay, clearly we don't have to know what these are, it doesn't really matter, and that gives us our equation as given down here. So the equivalent pore channel diameter, the hydraulic diameter if you like, is simply equal to the voidage divided by the specific surface area times by the solid concentration, or 1 minus the voidage. And that is a very major equation, a very simple equation, but a very major equation, which was really Kozeny-'s idea that he brought to the party to be able to solve the problem. So that was it. That equation there is substituted into Hagen-Poiseuille. The only other thing I want to mention about the derivation is the velocity, because clearly, really, we should be talking about the velocity through a pore channel. So if you like, the porous media was conceptualized as being a whole load of parallel capillaries, and from Hagen-Poiseuille we need the velocity through those capillaries, and that's not something that you conventionally measure, but where you do conventionally measure the superficial velocity, because that is the volume flow rate divided by the cross-sectional area of the bed. So that's the easy thing to measure. So in the derivation, the interstitial velocity is used, but the interstitial velocity is simply equal to the superficial velocity divided by the voidage. We know it's going to be a much faster velocity than the superficial velocity, and the voidage is always fractional. Okay, at the limit, of course, U would be equal to U0 when the porosity or voidage is equal to 1. So the Kozeny-Carman equation essentially comes from Hagen-Poiseuille with those substitutions made to it. That's one approach, and Kozeny-Carman, the equation originated from around about the 1917, 1920s time, so it's 100 years old, or over 100 years old equation. In the 1960s, these two people, fluid mechanics people, came up with an alternative way of calculating what is in fact permeability from the Navier-Stokes equation, and it's a very elegant derivation. There's a book that describes the low Reynolds number hydrodynamics, describes the derivation from the Navier-Stokes. It's under the conditions of creeping flow. So again, we make the assumption that there's no turbulence of any significance. However, using the cell model, they were possible to arrive at a solution to the Navier-Stokes equation where the permeability is equal to this function of concentration. Okay, so we're working in terms of concentration rather than voidage here, and also the SOTA mean diameter, the particle size. In their case, they were using uniform monosized spheres, but the way we translate that to something useful is that we use the SOTA mean diameter, and of course it's the diameter squared, which will give us the expected units of meters squared for permeability. So this is an entirely theoretical equation for permeability, unlike the Kozeny equation, which is really one that has a Kozeny constant, which we're not sure is 5 or not, whereas this is entirely a theoretical equation. And much like Stokes' settling equation, which again was a solution to the Navier-Stokes equation, I like to think of this approach as being absolutely analogous to the Stokes' settling equation. So we could, if we measured permeability, we could actually work out the particle size of the porous media. Just as if we measure settling velocities, we can work out the settling diameter of the particle. So other permeability models do exist. The two that are in common use, though, are Kozeny-Carman, because it's been around for a long while. It's a fairly simple equation to use, so it is used mostly. Happel and Brenner deserves to be used more because it's a thorough and fundamental derivation of permeability from the porous media. And I'm sure we will be seeing that more and more. However, in both cases here, there are really for a porous medium that is reasonably well packed, relatively high concentration. If you have open beds, or what's called loosely consolidated porous media, for example in sedimentation, that's a moving, loosely consolidated bed, or possibly even fluidization, again loosely consolidated and moving. If you have dilute media, which is loosely consolidated, then there's the possibility for the flow of the fluid to encounter less surface than it would do as if it was strongly consolidated. In other words, the pressure is probably going to be less than you anticipate. The pressure drop may be less than you anticipate. However, you may well also end up with some degree of turbulence, which could operate in the other direction and give you additional friction losses and therefore additional pressure. So when it comes to loosely consolidated materials, use these two equations with some degree of caution, and I'll say more about that in chapter 6, which is the hindered chapter, where we have porous media again, but it's not in consolidation, it's relatively open, typically in a sedimentation.